The audio should be working now, right? Yes, the audio is working. Great. Let's dive in. So, my plan is to pretend that Newton doesn't exist. And so we're going to try to, well, we're asking ourselves a question. We want to figure out how fast things fall. How would we do that in Excel? All right, goal. Figure out, actually, no, this is Excel. Everything becomes a table. So we're going to zoom in a little bit so everybody can see all the things. Whoa, 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 great. That should be close enough. Figure out how fast the things fall. Great. And of course we can cheat by just like looking up Newton's formula. And we're gonna, well, okay. Step one, we're gonna pretend this is a real experiment, even though it's not. We're gonna pretend. Step one would be to gather data, right? So we would like, well, we're going to have to simulate that because I'm not actually going to go out and drop a bunch of things off of different buildings and time things. So we're going to simulate that today. Simulated. Step two is going to be regression models. Do you know what a regression model is? If not, I'll show you. And since this is simulated, we're going to pretend that I'm two different people for each of these parts, right? This is Joe's job. And this is Harry's job. And when we do the regression models, we're going to figure out a formula. Such that if we give the computer a time in seconds, then the computer can predict how far something has fallen. That's the goal, right? Like this is what Newton did for us, and he did like Cartesian planes and things or something. I don't know, whatever he did. But we're going to do it with regression models. Great. So step one. No, hold on. I like to label like everything. The plan. So we're gonna we're gonna create. This is our table of observations, and we have to pretend that these things are real, even though they're not. But that's okay. You'll forgive me. The thing is, we could make this a real thing in real life. So we're going to create observation IDs. And in honor, oh, this is small again. Here you go. In honor of Mr. Newton, we're going to call them Apple 01 and Apple 02. And we're going to go all the way. We're doing science. We need a bunch of apples. Let's do what? 100. Let's do 100. Boop, boop, boop. Great. And so if we were doing an experiment, how would that look? It would look like this. Let's say we lived in a town where we had some different buildings and there was a cliff close by and we knew the heights of all of these. And so so what we're going to do is we're going to go to the tops of these different buildings and cliffs, and we're going to drop apples from each of these, and we're going to time how long it takes to hit the ground, right? So drop height. So every single time we drop an apple, this is something that we already know. How high it was, how far it fell, okay? And since this is a simulation, here, let's come over here. We're gonna create some different buildings. 1, 2, 3, 4, and 5. Great. Actually, I like to center like everything. This is something I picked up from my business analytics professor. All right, so there's 5 different buildings we're playing with. One of them is 100 meters tall. Boop. One of them is, I don't know, 200 meters tall. One of them is 150. One of them is just 25 meters tall. These are mostly big buildings, and one of them is just tiny. It's like practically a house or something. I don't know, 10 meters tall. Great. So we have these 5 different buildings. Now, here, why don't we do it this way so that everything is super visual? We're going to so each of these apples, we're going to randomly assign which building it gets dropped off of. And since there's 5 different buildings here, what we're going to do is we're going to make a column here of building chosen. And this can be any of the 5 buildings just at random. And the way we're going to show that is by doing rand between. And the smallest can be is 1, and the biggest can be is 5. And the way Excel works is it'll choose an integer between those two. So it's 1, 2, 3, or 4, or 5, right? And we can refresh this, and it'll, just cycle through. Great. I'm refreshing by pressing F9 on Windows. On a Mac, you would have to press function F9. Great. I'm going to double click this so that it goes all the way down to the bottom. Great. Now the thing about Excel is that these numbers, whenever we tell Excel to do a random number, then every time we update any cell, hello, it updates all of the random cells, hello, which is, sometimes annoying, but that's okay. We can work with that for now. Okay, so now, this is my favorite, formula in all of Excel. It's called Vlookup. If you haven't heard of it, it's very confusing, but it's worth a lot. Okay, so we're going to use the Vlookup function. And we're going to use these IDs to choose, so each of these IDs corresponds to a different height, right? Okay, so Vlookup, we're going to look up the ID for apple number 1, which right now is 4, but that'll change. Okay, and then, so we tell it, look up whatever's in cell B2. Then we press it common because it needs to know more stuff. Where are we going to look this stuff up? Well, the place where we have all the information where we can look this up is over here, right? Like this is where all the information is. So we tell it this is where the table is. Like imagine this, it's saying, we're telling Excel, hey, I've got this word. I want you to look it up in a dictionary. Except instead of that, we're saying we have this building ID. We want you to look it up in the building ID table. Great. So it's going to automatically look in the first column that we tell it belongs to the table. In other words, it's going to look here until it finds whatever, what was it before? It was like 4 or something. So it's going to come all the way down to 4. And then we need to tell Excel how many columns to go over from there. And the answer is 1, but it needs to go to the second column. So we write 2. Whoops, another comma there. And then we want exact match. Great. If you've never seen the Vlookup before, well, now you have. And we're going to double click this. And now look at that. So while this is 1, it pulls this 100 over here. And while this is 2, it pulls this 200 over here. And this 3, it pulls this 150 over here. Isn't that beautiful? All right, great. Now, this is where, so all of this like makes sense. And we could do this rolling dice and stuff. And I just use fancy Excel stuff. But let's pretend, so now we need to pretend that we went out and we actually measured all of these recordings. Like we decided we're going to do all of these different, drops, and we're going to drop it from the top each time. And we're going to record how long it takes to fall in seconds. How do we do that? I don't want to go out and actually do it. So we're going to cheat, and we're going to use Newton's formula. This is okay because after, this is just like the simulated experiment. Somebody could actually do this and go out and do the recordings, and that would be fantastic, and that would be more fun data to deal with. But we're just going to pretend that this is real data. So first of all, let's figure out, according to Newton, right? This is going to be like a circular Excel thing where we do one thing and then we end up doing the other. We do it one way and then we do it backwards. Okay, but whatever. So the formula we're ultimately using is distance equals 1/2, wait, no, equals velocity times time times 1/2 times a times t squared, right? Does that ring a bell? Hopefully. And for us, since our starting velocity is always 0, so it's 0 times time, okay, so times 0.5 times the acceleration is 9.8 meters per second times t squared. Great. All right, we can reduce that a little bit. So distance is going to equal 4.9, because, you know, the 0t disappears, and then half of 9.8 is 4.9 times t squared. Great. But the thing is, we have distance. What we don't have is time, right? So we have to shuffle some things around. So distance divided by 4.9 equals t squared. Great. Let's just flip this around so we know what we're doing. T squared equals distance divided by 4.9. Okay. And then we take the square root of that. So t is going to equal the square root, we're going to just do it like this, of d divided by 4.9. Does that make sense? So, because we have the distance, we're trying to figure out the time, and the way I did this, we can practically just copy and paste this over here. Great, like that. Except for the bit where it doesn't recognize d, of course, so we need to tell it what is the actual height. It's this right here. See that? So it's going to take this. It's going to take 100 divided by 4.9. Then it's going to take the square root of that. And this is the time in seconds that, you know, it's going to take to fall. Now that's like if we were to measure things super, super accurately to however many digits, right? And that's not going to happen. We need to add in, like, when I go out and measure this, I expect that, you know, I'll be on average accurate, but also I'm going to be a little bit delayed, and well, actually, yeah, I'm going to be on average a little bit delayed by like a tenth of a second, plus or minus another tenth of a second. And that's going to be the error terms that we use, and we're going to see if this works or not. But the way we're going to, so we just need to tell Excel, hey, more or less this. The way we can do this is by adding in another function, normal inverse, and this is stuff. So this is a probability normal curve. If you're familiar with that, don't worry. So on average, the average amount that things are going to be off by is 0.1, because I said so. Plus or minus about another 0.1, 60% of the time. 95% of the time, it's off by 0.2. Okay, so I'm pretty accurate. Not terribly accurate, and always, and generally I'm late. Actually, how about this? How about I'm not always late. Sometimes I'm on the money. Let's call this 05, you know? Yeah, 5% of the, I'm about 5% late, or 5/100ths of a second late, usually, on average. Okay, so there you go. Now we can drop that down and see how these numbers reflect human error. See that? Right? Because if we drop it 150 feet, the time should always be the same. Give or take a little bit. We're kind of accurate, but also not entirely. But, you know, not that bad. This is always basically 5.6, you know? Which is great, because that's I'm accurate to about a tenth of a second is what this is telling us. And that seems about right. Like, have you ever had a stopwatch and try to stop it on the exact right millisecond? Usually you're accurate at least within a tenth of a second, right? So I don't think that's unreasonable at all. Great. So this is great, and we can just, all these random things are changing all the time. Great. So this is going to be the data that we went out and collected, theoretically. I'm wondering, is anybody in the chat? Boop, boop, boop. Nope. Nope. That's fine. I'm all by myself. This is still fun. This is what I do with my free time. Great. So what we're going to do is we're going to pretend that this wasn't randomly generated by Excel stuff. We're going to, who collects in that many digits? Nobody does. So we need to bring this down a little bit. Hey, I want to bring this down a little bit. Did we go into the hundredths of a second? Yeah, we'll say we went into the hundredths. Great. But we weren't more accurate than that. We just are doing our milliseconds? Tenth, hundredth? No, hold on. How many zeros do you... I suppose we would need to go another decimal to get milliseconds. Am I confused? I might be confused. That's fine. It's fine. It's fine. Okay, but let's pretend that this is the data that we actually collected. We didn't generate this in a spreadsheet, but somebody went out and collected this. And, I think it would look pretty much like this. Okay? So now we have to forget everything we did and pretend that someone went out into the field and they dropped stuff off of building 2, 4, 4, 5, 5, building 1, building 2, building 3, these different heights, and they collected these different times, okay? And then they went to their statistics buddy and they said, hey, I got all this cool data. It looks like this. Boop, 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 boop. Let's make it look a little nicer. Let's make it, formatted right. Now look, so I copied and pasted it so that it just takes the values. It doesn't take the actual formulas. So this data isn't going to change anymore. So it really looks like somebody went out and they just collected data, right, on this. They dropped 100 apples off of buildings, 5 different buildings, randomly selected, and they recorded how long it took to hit the ground. And this is what they got. And I don't know why this did it like this. I don't want that many decimals. And they collected it to 2 digits after the decimal. Interesting. All right. So now, if I was a statistician, somebody's asking me, hey, I want to know how far something falls in a given amount of time. Like if I give you time, how far is it going to fall? We did it backwards in the experiment, but that's just because it's easier to do it that way, like record when something hits the ground after falling at a set distance. It's easier to tell that than it is to tell we're going to give it 2 seconds to fall and then measure how far it went. That'd be a little bit trickier. So, but the relationship should be the same, right? In theory, well, maybe, who knows? But whatever. We're a statistician. We got the data. We do what we're told. First thing I want to do is I want to bring this over to the other side, because what we know, we'll get rid of this. What we know is that we're going to start with a time, and then we have to predict how far it'll fall in that amount of time. So this is our x, and this is our y if we were to create a scatter plot, for example, right? And let's actually do that. And this is how you can tell that this was some pretty artificially generated data, except not so much. Remember, so the y-axis is the height of the different buildings, okay, and the x-axis is how long it took. And remember, these things didn't vary; these were always the same, and that's why we have these very horizontal clusters. Because when it comes up to a particular height, then it has a bunch of different data points that show up. But we have our human error, and look, see, at each of these different heights, it's spread out. It's spread out, which is interesting. And so here's the question that the statistician is going to ask. He's going to ask, is there a line that these things tend to follow? Well, it's almost a straight line. It also, there seems to be a gentle curve there. All right. So why don't we do this? Right now, we're just kind of casually exploring. We're going to try fitting some different trend lines to this scatter plot. This is kind of taking a shortcut. There's more rigorous ways to do that, and we're going to do the more rigorous way at the end of this. But okay, so here's our plot. here's our scatter plot, and this is the data. This is the relationship between how long something had to fall and how far it went. We're going to come in here and we're going to say, hey, why don't you give me a trend line? I did that add chart elements all the way down to trend line and over here. And we're going to hit linear. Also, there's a measurement of how accurate a line is. We can display this on there. R squared, actually, we're not going to use the equation right now. We don't need it. So R squared is a measure of how close the data is to fitting the line. And higher is better. This is kind of like radio signal, I suppose. So this is actually really high, 97.9% accurate, if you will. But also, look, it seems to not quite fit. Like all of these are over on this side, all of these are over on this side. This is below, and this is on top again. On top, below, 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 on top. That's interesting. Let's try a curve. We're gonna try a curve. Hold on. We'll come down to our trend line. More trend line options. Bring this over a little bit. So these are all our different curves that could exist. A lot of things are logarithmic. Ooh, interesting. Why is it giving me a hard time? I don't know. We're going to get rid of this one. Okay. And we're going to look at what if this is logarithmic. That's not how I wanted it. I want it to be exactly the opposite. Oh, exponential. Okay. So this seems to, let's compare R squared here, 0.972. That's actually kind of similar to before. And so this is actually pretty close again for a lot of data sets where it seems to be mostly falling on the line. But this is physics. Things should be like perfect. All right, so let's try something like this polynomial. And there we go. Our line is going straight through the center of each of these. So this tells us that there's some square action going on, basically. All right, so as a data analyst, what I think is the drop height is related to the square of time. So I'm going to just add in this column and go time squared. This equals that squared. Why is that a horrible number? Why do you do this to me? Why? What are you? Oh, because yeah. All right, because you hate me. Great. Bring this all the way down to like 2 digits because who needs to be more accurate than 2 digits? Certainly not me. Great. So this is time. 6.3 times 6.3 is 39.67-ish, right? 2.27, yada, yada. Remember, all of these digits, all these numbers are preserved in the original all the way out to the amazing decimal points over here. And that's because that's how Excel likes to do things. We could fix that in theory. Do we want to fix that? No, I'm too lazy. Great. Now this is my favorite part. So what we're going to do, I have a plugin installed onto my Excel, which is, it's hibernating on most people's Excel. I'm not going to show you how to get it activated on your Excel right now. But if you're interested in doing this sort of stuff, then you should look up regression on Excel and regression setup or something like that. Great. So what we're going to do is we're going to go into data analysis, and there's all these different things that show up. Excel's like, oh, I can analyze this data all sorts of different ways. And now I have my phone going off. That's nice. Great. Thank you. That's lovely. Oh, please be quiet. Thank you. Yeah. So, let's come down to regression. That's the one I'm interested in, right? We're gonna press OK. And basically, what this is we're saying, hey, Excel, I want you to predict some number. I'll give you a couple numbers, and I want you to predict another number. The number that Excel is going to predict is called our Y, right? That makes sense. Like this is just basic functions. And so it's, and the way that we're going to teach Excel how to predict these things is by giving it a bunch of data to already work with. So these are all of our Ys, and I select all of our Ys. We also have a bunch of X's. I have 4 X's. No, okay, so X's for Excel. These 2 columns are our X columns, okay? In other words, what we can do is we can tell Excel that, hey, if I give you a 6.3 here and a 39.67 here, then I expect a 200 out. If I give you a 2.27 and a 5.14, I expect a 25. If I give you a 2.34 and a 5.46, I expect a 25 again, all the way down. And we're going to ask Excel, hey, do you see a pattern here? Do you see a pattern where I could give you another couple of numbers and you would be able to spit out an answer for me? I'm going to hit this labels thing because I included labels in the data that I gave it. Like if I tell it time squared, I can't expect it to print out the words drop height because it doesn't understand English. We want it to just, it only understands the numbers parts. Okay, so the first row is labels. We told Excel that, and we're going to tell it to look for patterns in all of these relationships. Like if I give it these 2 numbers and it spits out that, if I give it these 2 numbers, it spits out that. Is there a pattern as you go down that you find? And do all that analyzing. We'll just click that because I like that. Do all that analyzing and give me a report on a brand new worksheet. And then I press OK. And it does it for me. And this is the report it gives me. This is stat stuff. And this is our regression model. I don't understand why it prints out the report on the sheet before instead of the sheet afterwards, but just to keep our chronology safe, we're going to put this afterwards. Okay, so this is the summary. It gives us all sorts of information. And what's important and what's not. Well, for our purposes, the most important things, okay, so R square and adjusted R square are things that refer to how accurate this relationship is, like how this is an indicator of, hey, if you can give me your 2 X variables that you gave me 100 different times, I'll give you a Y variable and it'll be this close to what's actually going on, more or less. But Excel also tells us enough in this report so that we can walk away with a formula so that we can do the exact same predictions. And that formula, oh, wow, that's really interesting. It has an intercept. That formula is going to be this plus times this plus time squared times this. In other words, that formula, distance is going to, hold on. Why don't we do it like this? Equals concat. This is just a way to put strings of text together. Distance equals this plus, whoops, yeah, we want that as a string, plus this plus, is this going to do what I want it to do? No, it's not. We need to start putting in quotation marks so it knows what's string, what are letters and what's numbers. All right, distance, da 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 da. That's an actual thing. This. Plus that. Oh God. gosh, this is not as easy as I thought it was going to be. It would have been easier just to type it out. That's fine. Plus, oops, times, there, like that. This is going to work out. All right, so distance equals B17 plus time, A18, times the time. I mean, times this coefficient, okay. Plus, this is not how Excel, this is not what Excel was built for. That's fine. Times this. And doesn't that look hideous? Yeah, it looks hideous. All right. But, all right, so it equals negative 1.6 plus times 0.4 plus time squared times 4.7. That's not exactly the formula, which is interesting. And part of that has to do with, well, how inaccurate I was in my data. Remember how I was always late? So it's going to try to predict a little bit over. I mean, on average, I was a little bit late. So it's going to try to predict a little bit over. So this kind of shows the strengths and the weaknesses of regression models. The strength is, well, hold on. We're gonna do something real quick. Also, this is one of my favorite columns right here. This is called the p-value column, and this, in simplest words, the way that I like to explain it, I'm not sure entirely how accurate this is, but I think it pretty much communicates well what's going on. This is these are percentages, okay? In fact, why don't we just convert these to %? Great. And we can add a bunch of zeros until we start seeing zeros. It's going to take a long time with this one. I don't think we're going to get to it here, but there were zeros at some point. Where were those zeros? Oh, we'd have to go 40 zeros and then 39 zeros, and then it's going to have a 9. Don't feel like doing that. So for all practical purposes, oops, no, I didn't want that. There, accounting, interesting. I didn't know you could just press that button. Great. This is how likely it is that, this could also just be a 0. So Excel says, hey, there's kind of a 56% chance here that this is really a 0. And there's a 77% chance that this could also be a 0. So we might be off on these two. But Excel is really convinced that there's a strong relationship between how far something travels and time squared. Which is interesting because remember our reduced formula over here? Distance. Everything else became zeros, right? This became a 0. Right? Like all that we had was this times time squared. So there's a couple disadvantages with using regression models. First of all, like, hey, we're not exactly right. We've got a pretty good estimator here, but this isn't as accurate as what we started with. But it's fascinating to see how Excel was able to tell us where the important variables are, and pretty darn close to what those actual variables are, to how that relationship works. And we were able to do it with just a couple clicks. Fundamentally, like this took a little bit longer to set up, this part right here. But then when we got to stat stuff, like we created a new column, and then we played around with the scatter plot a little bit, and then we clicked on regression models. So the way that Newton learned about the gravitation formula of how far something travels when we drop it on Earth, like he understands a little bit better what's going on and why things travel as fast as they do. And that's not something that we can learn from a regression model. But what we can do with our regression models is we can pick up these relationships a lot faster. you can have uh, uh, you can have up to 16 different x's in Excel, and say, hey, if I give you these 16 different x's, can you predict the y for me? Which in other words, like, we can, with just a couple clicks, learn about much more complicated relationships than Excel, than like puzzling out in theory all the different things. In fact, here, why don't we real quick? So since based on our regression model, time isn't important. There's nothing you can do about intercept. Intercept's always going to be there. But since it said time is very likely could be a zero, like, why don't we try running a regression model without time? We'll just say, hey, Mr. Excel, I'm going to go do my regression. And a lot of these things are the same, but I'm not going to tell you the original time. All I'm going to tell you is time squared. Whoops. I'm not, okay. So this is all of my y values again. This is the drop height. This, you probably can't see this very well because it's super tiny, but this says column E from cell 1 to 101. That's what we want to get out of this formula that you're going to try to make up for us. And we'll tell you what's in D, right? So when I give you 39.67, I want to get a 200. When I give you a 5.14, I want a 25. When I tell you 5.46, I want a 25. Again, with the same formula. Good luck. And we'll see how Excel does. I'm really curious. I don't know how well it's going to do. Boom, even closer. It's starting to realize that this is a zero. But remember, since we, on average, we overestimated with all of our measurements, this is really kind of impressive to me. Yeah, it's even more convinced now. Remember, so in our first regression model, it was, let's put this back at general again. How likely? Whoa, settle down, friend. Thank you. General. So this was 39 zeros and then a 9. Now, let me zoom this in. This is 121 zeros and then a 1. That's the odds. That's how likely Excel says that's the chances of this being just a coincidence. So there you go. There you go. I think that this also went up, our R squared. 99.66 versus 99.66. Yeah, that's basically the same. All right, never mind. Excuse me. But there you go. There you go. That is, I'm glad this all worked for my little experiment. We already knew what the relationship is supposed to be. Look, it's even closer to what the relationship ideally is supposed to be. And so this data, like, it's kind of trivial in many ways because like we already know what formula is supposed to look like. But this is a good example of, like, we can get a data set where we think there might be a relationship between two different numbers or between a bunch of different numbers, and we don't know what that relationship looks like going in. And we can use Excel to figure out what that relationship might be. So there you go. This is what I like to do in my free time. It's a lot of fun. Excel's a powerful thingamabob. Oh, you couldn't really see what was going on there. Here, that's better. Did I get any comments in this whole time? Nope. That's fine. All right. That's my story. I'm going to get back to homework now. Oh, geez, it's so late. I'm going to get back to a little bit of homework, and then I'm going to go to bed. Because I'm tired. Great. All right. Thanks for tuning in. God bless and ciao.